Hi guys, in last class we discussed about inclined motion. So we got an expression for angle of repose. Today's class I would like to find acceleration of a moving object in an inclined motion. So this is a question, acceleration of a body sliding down in an inclined plane. Let us try to find acceleration. So what you are seeing, so this is an adventure sport called as, they call it as raw run. So it is a very dangerous adventure sport. So all the way downhill, the skater is moving. So he is moving with velocity, or he is having acceleration. That acceleration is due to because of the inclined plane. And let us try to find the acceleration of this moving object. So here we need to consider what are the forces which are acting on him. Suppose if I take a point where he is moving, so if we can write the sum of the forces which are acting on him. So there will be a resultant downward force. That resultant downward force cause acceleration on him. So let me take, this is a situation. Suppose if I draw an inclined plane. So this is inclined plane. So he is moving. So I will take him as a block of a small mass. So I'll consider him as a block of mass. So this is making an angle theta. So we know that that angle is known as angle of repose. Now, as usual, we know that there are the two forces which is acting. So right up there, this force known as normal action force R, and here the right down, so there is a force of gravity which is acting downward direction, which is known as mg. Now here the force mg is dissolved into two components. Suppose, so this mg is making a vertical component, this is known as mg cos theta, and the same horizontal component which is known as mg sin theta. And here there is a friction force which is acting backward, so this is the kinetic friction. So right in the wheels, the kinetic friction is acting. And if he is moving forward, it means there is an acceleration in the forward direction. So you think common sense. By using common sense, since he is having forward acceleration, it means some force is acting in forward. So that the force cause the object slides down gives the acceleration. Let us try to write the expression for that. So if I take the situation at here, if R is the normal action force which is acting, now if I take a coordinate axis, so I will draw the coordinate axis right at here. So if I represent this is a positive y-axis, and one more, here it is positive x-axis and y-axis. Now normal action force always acts perpendicular surface R, and very important force, that is mg, which is acting right downwards. So that is the force which acts mg, weight. Now mg is making an angle theta with the vertical axis. So this angle theta, so this angle known as angle of repose, and these two angles are equal. Now if this is theta, now mg is making component, this side goes to mg cos theta component, and this side is mg sin theta component. We learned that from vectors. Suppose if this is a vector is making an angle theta, if a bar is a vector making an angle theta to the horizontal, so the a bar having component which is known as a cos theta along the x-axis, and along this side it became a component a sin theta. Like here mg weight is also making an angle theta, so that's the reason mg cos theta, mg sin theta will be comes at here. Now if I include the friction force, since the block is moving, so there is a kinetic friction. So the kinetic friction F suffix k will be acts backward direction. So in this backward direction, the friction force F suffix k. Now if we can write, mg is perpendicular to the inclined plane, so it balances the normal action force. Here which are the forces are balancing? R is a force which exactly balances to mg cos theta. So we can mention that at here. First one, R equal to mg cos theta. These two forces are equal. That's equation 1. But when you can write, for the mg sin theta equal to f of k, if mg sin theta equal to f of k, if these two forces are equal, then the block will be at rest. Then the block will not move, it will be at rest, because some of the all forces are balancing, so there is no forward acceleration. But in our case, the block is moving forward, so it is having forward acceleration. So it is moving forward, means it is having forward acceleration. Since it is having forward acceleration, it means the mg sin theta component applies more than the f of k. So the mg sin theta component is a force. So that is the extra force that causes acceleration in the block. So if you can write that, if I take, if F suffix k is kinetic friction, then the net force, acting on the block, so the net force causes the acceleration. So the net force F equal to mg sin theta minus F suffix k. So be careful while writing these expressions. So these equations you should write by thinking common sense. Again, if I repeat, suppose if this mg sin theta component is equals to f of k, as in this case, if mg sin theta component is equals to f of k, the object will at rest. But in our case, the mg sin theta component is not equal to f of k. So that's the reason the block is moving forward direction. If there is more forward force than the backward force, then the object moves in the forward direction. That's what happens. So just like in the tug of war, where the more force is there, so in that direction the object will move. So to find out the more force, we need to subtract the forward force minus backward force. So here forward force equal to mg sin theta, backward force equal to f of k. Here f of k is kinetic friction, and we know that, but f of k equal to kinetic friction formula, so mu of k times r, normal reaction, and substitute equation 1 at here. From 1, equation f of k equal to mg sin theta minus mu of k times r. So substitute r value at here. Therefore f of k equal to mg sin theta minus mu of k times it's mg cos theta. Now if I take this equation 2 and this is equation 3, now substitute 3 in 2. You can write 3 in 2 to get the resultant force. The resultant force F equal to mg sin theta, sorry, here I have mistaken, this is f of k, I already substituted, so there is no more further substitution. Since f of k equal to mu of k times r from 1, so here directly I can write this is f. Here mg sin theta minus f of k. In the place of f of k, I substituted mu of k times r. Okay, and in the place of r, so we substituted mg cos theta. So this is the final expression. But from Newton's law, but F equal to ma, force equal to mass times acceleration. So if you can substitute this value at here, ma equal to mg sin theta minus mu k times mg cos theta. Now take the m common factor. M times a equal to m of g sin theta minus mu k times g cos theta. So m gets cancelled on both sides, and the final expression for acceleration a equal to, I can take the g common factor, g of sin theta minus mu k times cos theta. So we got an interesting expression. The acceleration of a sliding object is purely depends upon theta and mu k. Of course g is a constant. So theta here we know that is the angle of repose. The theta what we got at here, so this is the angle of repose, and mu k is nothing but coefficient of kinetic friction. So the final expression for acceleration of an object sliding down in inclined plane, acceleration a equal to g of sin theta minus mu k cos theta.